Hello everyone. In this section, I want to introduce the perturbation theory for the degenerate cases. In the previous sections, I introduced the basic formulas of the perturbation theory. And first, we have these two basic assumptions. First of all, we assume we have solved the eigenvalue problems of the zeroth order Hamiltonian, which is the H0, and we want to solve the eigenvalue problems of the H. And we want to expand the H's eigenvalues and find their corrections by orders. So we expand them and we label each orders by lambda. En equals to En0 plus the lambda E and En1 the first order and the lambda square En2 the second order. So does the state En. By compare the coefficients of the lambda k, we derive the basic equations Hz like this. H0 ENK plus H1 ENK minus 1 and equals to sum P from 0 to k ENP and times ENK minus P. And we get the basic formula. Find the case order's energy correction ENK equals to this. And the state corrections can be labeled as is like this: sum m en0 enk em0， and we need to calculate this. And in the previous sections, we assumed the ENs are pairwise different, which means there is no degeneracy. But in degenerate case, it will be a lot different. So let's begin. In degenerate case, we first of all assume En0 has the Gn fold is Gn fold degenerated for 0 Hamiltonian H0, and if we restrict to it's the eigensubspace, which is Vn kernel. Subspace, and its eigensubspace is a Gn dimensional. It's a Gn-dimensional linear space, and in this we can find a orthonormal basis. Can find a orthonormal base phi n alpha. Alpha is 1, 2, and Gn. And we have the equations phi n alpha, H0 phi n alpha equals to En 0 phi n alpha. Alpha equals to 1, 2, and to Gn. And now we want to restrict to this eigenspace and consider the eigenvalue problems of the H1. And we restrict on this eigen 1, and we solve the eigenvalue problems H1. The ENX0 equals to E1. And here the E in x0 is a linear combination of the finding alpha, which is the base of the this sub-eigenspace. So we also have the h0 x on the en x0 equals to en0 en x0. And we have the basic and in the first degeneration case, we assume the E and x1 are pairwise. Different, which means the h1 can remove the degenerates. But if we remove the restriction of from the eigensubspace, we have these equations h1 en x0. The en x0 is no longer the eigenvector of the h1. We have the en x1 en x0 plus m not equals to ny cmy. And this still remains unknown. These states are the state that not belongs to the sub-eigenspace of the eigenvalue en0. But we still have some orthonormal relations. Orthonormal relations is the en x0 en y0 equals to delta xy. The en y0 h1 en x0 equals to en x1 delta x1. And for em y0 h1 and x0 equals to x1 x0 plus prime y prime c prime y prime y prime y prime 0. Oh, here m represents the m's, emy represents the eigenvalues of the em0, and the y labels the degenerate. If em is also the degenerate, the y can label the different eigenvectors with back to the same eigenvalue em0. So this equals to cmy. still remains unknown. And we consider the first order perturbation theory. We recall the first order perturbation. The formula of the first order is equal to m1 0 plus en1 0, and here we replace en0 to enx0, h1 enx0. And first of all, we left act enx0 equals to x1. When we can find these two terms will be cancelled, since h0 acts on this term becomes 2 and 0. So we have the first formula, enx1 equals to x0 enx0. And here the enx1 also satisfy the definition of the here. This enx1, they are the same because the enx0 are also the eigenvectors of the Hamiltonian h1. So this could enx0. So this is the first order energy correction. And then now we want to find the state correction. Find the state correction in x1. And enx1 can be expanded in this way. We want to expand them by the x1 plus sigma m naught equals to ny em0 e nx1 em0. By calculate, we need to calculate these two terms. First of all, let's calculate the inner product of the EMY 0 to ENX1. We left act the EMY state EMY. We have the basic equations. We act the ENY from the left on this equation. So H1 ENX0 EMY0 H0 ENX1 and 0 plus ENX1 this equals to delta y x, since y not equals to x, so here 0. This term vanishes. And this term, because e and x are also the eigen. And in this term, this left action goes to em 0. So we can get the zero equals to en 0 minus em 0, and this is em y 0 h1 enx 0. So we find this term, and we need to calculate the inner product of the eny and the enx1. In this term, in the first order perturbations, we may find we left act on eny, so we get we have eny 0. And in these equations, we may find that these two terms cancels, and these two terms are also cancelled, because if we read, this is the h1 x on the on h0 enx0, this equals to nx1 enx0 plus cmy emy. We may find these two terms are orthonormal, so they vanish, and the rest of these two terms will be cancelled. So we didn't get more. We need to get more informations. So we need to consider the second order perturbation. In the second order perturbation, we write the basic equations. h1 0 enx2 equals to enx0 0. This term is 0. And we take the left actions on the enz0. So this term becomes 2. First of all, we find these two terms will with these two terms because will be cancelled because the z0 equals to x0, and we have the equation. Then this term comes to delta xz. So we move this term from right to the left. We have the basic equations 1 and x1. And we can here we just insert and we can expand the en(x1) equals to so from m not equals to ny plus some y not equals to x so and we so these equations becomes to z0. The first term of this equation in z0 h1 then en(x1) equals to h1 em(y0). The em(y0) en(x1) plus 1 and x1 because and this term is because these are all the under subspace of the en0 eigenvalues. So this term is equals to delta yz enz1, the first order. So it becomes quite simple. C1 so the equations becomes 2 so the complete so this equation and the way finishing this equation is equals to enz1 minus enx1. And we divide this in two situations. The first situation, take z equals to x. So we have the second order energy correction equals to z equals to x. This term will vanish. Equals to y0 in x1, and this term we have calculated before, and it equals to what's here? Calculate before, we just insert this term equals to EMY0 h1 nx0 over En0 minus Em0. And we take, and in second situation we take z not equals to x. So we have the equations y and z. So we find the ENZ0, the inner product of ENZ0 x1 equals to y and the 0 x. ENX1. So we just, and this term we have calculated before is this term, and we write it complete. So we find the first order correction, and x1 equals to sum m naught equals to y and we sum the z naught equals to x in 0 e x1 z0. The first term is the correction term that is not the eigenvectors of the En0. So it is the same form. It has the same form of the non-degenerate case. And the second term is due to the degeneration, due to the effect of the degenerate. Which is the second order perturbation. Okay, in these sections we have solved the perturbation theory problems of the degenerate case. In the first case of the degenerate, which means that H1 removes the degeneracy. In the next sections, I will introduce the perturbation theory for the case that H1 does not remove the degeneracy, which is the very common in the scientific research. So, today is over.